The second video in the Kinetics series will address rate laws. The objective covered in this video is to evaluate data to determine the form of the rate law, or what we call the rate order. As you already know, when we studied equilibrium, we found out that chemical reactions are reversible. Oftentimes, as products are formed, they accumulate and react to form what was the reactant. From our previous example in video number 1, 2NO2 yields 2NO plus O2 gas. As NO and O2 accumulate, they can react to reform NO2. Now the change in NO2 depends on the difference of the rates of the forward and the reverse reactions. But don't get scared here, because that sounds really complicated, doesn't it? In this unit, we will not take into account the reverse reaction. We will only study the rate of the initial forward reaction of all of our examples. If the reverse reaction can be neglected, the reaction rate will depend only on the concentration of the reactants. A rate law shows how concentrations relate to the rate of the reaction. Some concentrations directly relate with rate, and some are related logarithmically, and some are even related inversely. But we use the equation rate equals the negative change in A, which is the reactants, over a change in time. This is what we talked about with average rates, but now we're going to set this equal to K times the concentration of A to the n power. We use this equation to determine what we call the rate law. In this formula, A is the reactant, K is the proportionality constant, and N is what we call the order of the reactant. Both are usually determined by experiment. Most simple reactions, the rate orders for any reactant are often positive integers, but they can also be 0 or even a fraction. But we will study the 3 rate orders of 0, 1, and 2. Again, the concentrations of the products do not appear in the rate law because the reaction rate is being studied under the conditions where the reverse reaction does not contribute to the overall rate of the reaction. So here's where things can get a little confusing in this unit. The value of the exponent n must be determined by experiment. So often our examples have data that comes directly from some kind of experiment. It cannot be determined by just plugging something into a balanced equation. The rate law constant is dependent upon the species in the reaction. What are their shapes? What are their components? What are their potential energies? And there is an infinite number of combinations of reactants. So experimental data is often used to determine the rate law for any given reaction. There are 2 types of rate laws, or ways to determine rate order. The first one is the differential rate law, and this one is simply just called the rate law most of the time. It shows how the rate of a reaction depends on concentration. So how fast the reaction goes depends on the concentration of the reactants that you started with. The second type of rate law is called the integrated rate law, and this shows how concentrations of species in the reaction depend on time. So how long has the reaction been occurring before we can determine what the concentrations of the reactants are? So they're definitely related, but they have a different perspective. And those of you that know calculus, these equations and formulas that we use in this unit will probably make some sense. But for those of you that have not had calculus, never fear, you will still be okay. We have equations and so forth to help you through this. The differential and integrated rate laws, as I said, for a given reaction are related. Knowing the rate law for a reaction is important because we can usually infer the individual steps involved in a reaction from the specific form of the rate law. So how do we determine the order of a rate law? There's a couple different approaches that we can take. The first step in understanding how a given chemical reaction occurs is to determine the form of the rate law. Reaction rate form is often described as orders, for example, first order or second order, even 0 order. A first order reaction, the concentration of the reactants are reduced by half, then the overall rate of the reaction will also be reduced by half. A direct relationship exists between the concentration and the rate. However, second order and 0 order have relationships, but they're not direct. One common method for experimentally determining the form of the rate law for a reaction is called the method of initial rates. The initial rate of a reaction is the instantaneous rate that is determined just after the reaction begins, before the initial concentrations of the reactants actually have a chance to change significantly. To use what is called the method of initial rates to determine rate order, we compare results from a series of experiments with the same reaction. In the example I have on the slide, 3 experiments are run with the same reaction, but each experiment starts with a different set of concentrations of the reactants. As each reaction starts, the initial rate is measured to determine how fast the reaction runs prior to any significant changes in the concentrations. This table tells us that the initial rate of experiment 1 is 1.35 times 10 to the negative 7th molar seconds, when the concentrations are 0.1 and 0.005 with the reaction constant of K. So K is the rate constant. N and M are the rate orders of each specific reactant, and they can be determined by dividing the known rates. So let's use practice problem 2 to show how to use this method of initial rates to solve for rate order of each of the reactants. Find the form of the rate law for each reactant and the overall reaction order. So when the problem is asking for form, they are actually asking for rate order. To solve this problem, we need to compare the results in the reaction. So let's look at our data table. When I look at the results in this table, I notice that experiment 1 and experiment 2 used the same concentration of NH4+, but they doubled the concentration of NO2-. But notice that the rate also doubled when we doubled this concentration. So I'm going to take this relationship that I see and I'm going to put it into our equation. And when we do this, I want you to notice that a lot of these numbers will cross out in our calculations. So I'm comparing experiment 1 and experiment 2, and I'm going to choose the one with the higher rate to put on top of this proportion. So rate 2 over rate 1 will be equal to 2.7 times 10 to the negative 7th molar seconds over 1.35 times 10 to the negative 7th molar seconds. And these are both set equal to our rate law equation. K times the concentration of NH4+ to the N and NO2- to the M. So when we fill in our concentrations from the data table, notice that K's cross out and the concentration for NH4+ also cross out because they're the same. But our concentrations for NO2- double, and so does our rate. So we end up with 2 equals 2 to the M, which also means that M equals 1. So rate order of NO2- is 1. Now I'm going to go back to the data table and see if I can't find some relationships for NH4. When looking at the results for experiments 2 and 3, the concentrations of NO2- stayed the same and the concentration of NH4 doubled. Also, the rate of the reaction doubled when we doubled the concentration. So when I put this information into our equation, notice again that many of the numbers cross out, including our K constant. So M, the order of NH4+, equals 1. So N and M are both 1, but they are unrelated. These are specific to each reactant in this specific chemical equation. But the overall reaction order is 2 because we add the orders of the 2 reactants together to get the reaction order overall. Now that we know the rate orders for both reactants, we can use this to determine our rate constant K. You can use the information from any of the experiments in the data table and the solutions that we just solved for the rate orders. In this example, I took the solutions for M and N, which we just found, and placed them back into the information for experiment 1. So rate for experiment 1 equals 1.35 times 10 to the negative 7th molar seconds equals K times the concentration of 0.1 to the first and 0.005 to the first, which leaves us with K equals 2.7 times 10 to the negative 7th liters over moles, seconds. Now I want you to try this idea one more time and practice problem 3, but a little quicker this time. You can follow along on page 550 in your textbook. The reaction between bromate ions and bromide ions in an acidic aqueous solution is given by the equation BrO3- plus 5Br plus 6H plus yields 3Br2 plus 3 waters. Using the experimental data, determine the orders for all 3 reactants and the overall reaction order and the value of the rate constant. You should probably try to pause this video and see if you can work this out on your own before you switch to the next slide to get the answers. You should find that N equals 1, M equals 2, and P equals 2. The overall reaction order is 4. When this is put into the experimental data, K equals 8 liters cubed over molar cubed seconds. Note the unit for the K value. These units, unlike other reaction constants, need to be included. As a shortcut, you can always take the total reaction order minus 1 and use it as an exponent, but please notice that the liters are on top of the moles when it comes to the K constant. While this is a shortcut, you should look at your calculations so as to understand where the units are coming from. This concludes the second video in this series.